we're going to use numerical prefixes when naming our covalent compounds. If an atom just has one of a certain type of element, we'll use mono. However, a lot of names don't include the mono because one is understood. So it may be left out. Then we have di, tri, tetra, penta, hexa, hepta. These may sound familiar from math class. They're the same. Octa, nona, and deca. So our covalent compounds consist entirely of nonmetals. Once you're certain that you're dealing with a covalent compound or a molecule, all you have to do is use your numerical prefixes, and the second piece will get that "ide" ending like we saw with the ionic compounds. So we have carbon, and mono is understood. So there's a couple of examples like carbon monoxide, which is a deadly gas produced by furnaces sometimes. Sometimes we use the mono. In general, the mono is just left out. So it's not monocarbon, it's just going to be carbon. And then we have two sulfurs, so we're going to do disulfide. On letter B, we have sulfur, just one, and then two oxygens, so we'll do dioxide. In letter C, we have phosphorus, and then 5 chlorines, so we'll do pentachloride. And then we have boron, which is typically thought of as either a transition metal or non-metal. So it definitely falls into the category of being a covalent compound. So here I'll do boron trifluoride. So in this exercise, we're asked to come up with the formulas for some different covalent compounds. So there's two ways that I know I'm dealing with covalent compounds. One is I can check the location on the periodic table. Everything is on the right-hand side of the periodic table. The sulfur and the oxygen, for instance, all the way on the right-hand side. Second reason is once they start using numerical prefixes, you know you're dealing with a covalent compound. We don't want to use numerical prefixes with our ionic compounds. So silicon, dioxide, no crisscross required. Covalent molecules are much nicer. Phosphorus, trichloride, sulfur, trioxide, and dinitrogen trioxide. So the di and then the tri. All right, so let's practice naming covalent compounds a little bit more. In letter A, we have sulfur, and then 4 fluorine atoms. So we're going to call that tetrafluoride. And then in letter B, we have arsenic, and then 3 bromine, so we'll do tribromide. Letter C, we're going to do selenium. Keep the name of the first being the same, and then we'll do dioxide since there's 2 oxygens. 2 chlorines, so I'm going to do dichlorine, and then trioxide. In letter E, we have dinitrogen, And then there's 4 oxygens. So we might do tetra, but when you have an A next to an O, let me write it down and then fix it. So when you have an A immediately followed by an O, you're going to drop the A. So this is actually going to become tetroxide. Don't do AO back to back like that. For this one, we're going to do iodine, pentafluoride, next we have diboron, trioxide, we have 4 arsenics, so I'll do tetra arsenic, and then 10 oxygens, so that's going to be deca, but then we would have A followed by an O, so I'm going to drop the A, so I'm just going to do decoxide. In problem number 4, I can quickly identify all of these compounds as being covalent. And how I did that was by noticing that every single one of these names had some kind of numerical prefix. And remember, you're only going to see the numerical prefixes with your covalent compounds. Naming the covalent compounds, writing those formulas, is much more straightforward than what we have to do with ionic compounds. So we're going to just do xenon, and it's dioxide, so I'll do O2. Sulfur, it's hexafluoride, so I'll do F6. Dichlorine, trioxide, dinitrogen, tetraoxide. When there's an A followed by an O, then the A is dropped. Diboron, so 2 B's, trioxide. Tetraarsenic, so 4 arsenics. Decoxide, and so this is another example of the AO combination. This was deca, which means 10. In this table, we're dealing with both ionic and covalent compounds. So the first step is going to be to decide if it's ionic or covalent, so we can use the right approach when naming the compound or writing the formula. So cobalt is a metal and oxygen is a nonmetal. So this is ionic. With ionic compounds, I need Roman numerals, especially with their transition metals, and there should be no numerical prefixes. So I need to figure out that Roman numeral. So I know oxygen is a 2-, and it combined in a 1-to-1 ratio with the cobalt. So that must mean that cobalt's a 2+. Someone crisscrossed down the 2's and then reduced it. So I'm going to name this cobalt 2 oxide. In our next example, we have 2 nonmetals. So this is a covalent compound. And so we're going to do nitrogen, trifluoride. Diarsenic trioxide, well, once I see those numerical prefixes, we know it's covalent. Di means 2, and tri means 3. Sodium phosphate. So phosphate is one of our polyatomic ions. It's PO4 3-. And we're crisscrossing that with an Na+. So I can put some parentheses there, but there's going to be a 1 that gets crisscrossed down, a 3 for sodium. If there's a 1 outside the parentheses, you can get rid of both the 1 and the parentheses. So this is going to be Na3PO4. And it's ionic. Whenever you're using a metal and a polyatomic ion, we can safely classify it and name it using our ionic system. 2 nonmetals. This is going to be covalent. And this is 2 nonmetals too. So let's do both of these back to back. We have carbon. And then we have 4 bromines. So we're going to do tetrabromide. Here we have 2 iodines. So I'm going to do diiodine. We don't drop the double I's. You keep it like that. So we're going to do diiodine. And then we have 5 oxygens. So it's going to be pent. I'm going to drop the A. Drop the A from the AO combination. So we're going to do pent oxide. The next one is an ionic compound because I have a metal, which is lithium, with a nonmetal, which is hydrogen. The hydrogen's in the second position, so that means it's negatively charged. It's our anion. So we're going to do lithium hydride on that example. Iron 3 oxide, ionic, and I know that just from seeing that Roman numeral. You won't see Roman numerals with your covalent compounds. So we have Fe3+, the 3+ coming from the Roman numeral, and O2-. I need to crisscross those. So I'm going to wind up with Fe2O3. And the last example is ionic. However, it consists of 2 polyatomic ions. We have ammonium, which is NH4+, and sulfate, which is SO4 2-. I'm only going to put the parentheses around the ammonium because that's going to get a 2. We're going to be crisscrossing down a 1 with for our sulfate, but then you don't need parentheses. I'm going to do NH4 2 SO4 as our formula. And this is relatively new information in the grand scheme of things. 20, 30 years ago, I don't remember when, it was discovered that mercury ion exists as a diatomic ion. So mercury 1 has the formula of Hg2 2+. When you have to crisscross mercury 1, you're going to treat it the same way you treat your other polyatomic ions. So you'll have parentheses around the Hg2, and the 2+ would go on the outside of the parentheses. That also means that if the opportunity presents itself to reduce, you can't mess with anything in those parentheses. You can't reduce that 2 down, even if you wind up dropping the parentheses or anything like that, because it's part of the diatomic ion. That's mercury 1. Mercury 2 is a little bit more cooperative in that mercury 2 is just Hg2+. Some more practice naming our compounds. This looks like a list of both ionic and covalent compounds. So the first thing I'm going to do is label everything as being ionic or covalent. I'm going to use INC. I'm going to tackle my covalent compounds first. So we're going to do chlorine dioxide and iodine trifluoride. So now we have a bunch of ionic compounds to name. And I'm going to look through this list really quickly and decide who needs Roman numerals. So this one's going to need a Roman numeral, this one, and this one. And I'm just making these decisions based off of the location on the periodic table. Iron, copper, and cobalt are all transition metals, so they're going to need Roman numerals. So on the first one, we have calcium, fluoride, and I don't need a Roman numeral, and I definitely should not be using any kind of numerical prefixes because it's ionic. Get all the ones that don't need Roman numerals. So here we have potassium, and after that we have OH minus. So it's split up like that. OH minus is a super common polyatomic ion, hydroxide. And then another polyatomic ion in here, this is SO42 minus. This is going to be potassium sulfate. Now for the remaining three that need Roman numerals, I need to figure out the charge on the metal before the crisscross. So here, I'm going to put iron as a 3+ because I know chlorine does a -1. And if I redo my crisscross, I see that it's going to be a good match. So this is iron, 3 chloride. Take my time with this one. So let me start with copper +1 and sulfur 2-. And actually that winds up being a match because the 2 would go down here and the 1 would go down there. So this is copper 1. You're always going to use the charge on the metal before the crisscross. Sulfide. Here, I like when I have a group 7 in the second position, because I know it's just a -1, so most likely this number came from the metal. So this is going to be cobalt 3 fluoride. First, I'm going to do the types. Roman numeral, it's going to be ionic. Prefixes, covalent. Calcium's a metal. So this is ionic. Magnesium's a metal. Nitrogen triiodide, I see the tri, so I know it's going to be covalent. Dinitrogen, another numerical prefixes. Potassium fluoride, potassium's a metal, so that's ionic. So that's going to be covalent. Manganese is a metal. Potassium is a metal. Phosphorus and sulfur are both nonmetals. Bromine and fluoride, more nonmetals. Ammonium and nitrate, those are both polyatomic ions, and so that's classified as an ionic compound. And arsenic and oxygen, both nonmetals. From there, when I'm writing formulas, I have to do the crisscross on my ionic compounds. So let me do the covalent ones first. They're a little bit less work, no crisscross. So boron, trichloride, nitrogen, triiodide, and dinitrogen, tetraoxide. We're not going to reduce this because it's covalent. We're only really going to focus on writing our ionic compounds in their reduced form. If it's covalent, you want to show the molecular formula. So back over here, we have mercury 1 oxide. So I'm going to do Hg2, 2+, and oxygen is going to do a 2-. I'm going to put parentheses around all that, and then I'm going to bring this 2 down here and this 2 down here. Now I have parentheses Hg2, close parentheses, another 2 that came from the oxygen, oxygen, and then the 2 that came from the mercury. I stated earlier that we cannot mess with the stuff inside the parentheses. That's still true. But on the outside of the parentheses, we have a 2, and then we have a 2 here. So we could definitely reduce those 2's, which leaves us with Hg2 1O1. And then the final thing to say, the final way to write it, would be to get rid of the 1's and drop the parentheses. So my final answer for mercury 1 oxide, I'm going to write it over here, is Hg2O. And all of this is just my work to get there. Calcium phosphate, we have calcium 2 plus and phosphate 3 minus. I'm going to need parentheses, so I'll do Ca3 parentheses PO4 2. Magnesium's a 2 plus. Nitride, the ides are from the periodic table, that's 3 minus, it's in group 5. So my formula will be Mg3N2 after my crisscross. Potassium's a +1 and fluoride's a -1, so Kf is our formula. So I don't know about you, but I find the covalent compounds to be much more approachable. So I'm going to name those first because I'm just going to need my numerical prefixes. So phosphorus, trichloride, diphosphorus, trisulfide, bromine, trifluoride, and from our polyatomic ions we have NH4 plus and NO3 minus, so we're going to call this ammonium nitrate. Oh, I said I was going to do the covalent ones. That's still the correct name. Let's do this last one. Diarsenic pentoxide. Okay, let's go back and do these two. This one's not so bad because potassium's a group 1 and hydroxide is one of the polyatomic ions, but no Roman numeral. On this last one, we're gonna need a Roman numeral. Manganese is a transition metal. So I do know that sulfate is a polyatomic ion with a 2- charge. These are combining in a 1-to-1 ratio. So my guess is going to be that manganese has a 2+ charge, and that the 2+ and the 2- will cancel, and that's why they have this 1-to-1 ratio. Double check the crisscross, reduce it down, verify it for yourself. Make sure you know what this charge is before you write the name. So it's going to be manganese 2 sulfate.